Okay guys, today we're going to make another review booklet for physics. We're going to do this review booklet on the second quarter, so stuff we learned in second quarter. It looks kind of like this, the little booklet that you fold. If you don't know how to make it, I can help you fold one. But you got to have this information on it. So when you fold it, there's 8 pages. The title, the cover page is number 1. On this back cover here, it should be 8. So there should be 8 pages. So let's get started. I got 8 topics to review from that second quarter. On the title page, guys, this is everything that fits on the title page. So right on that cover, we're going to title it Physics Second Quarter Review. So title it Physics Second Quarter Review. And I'm just going to run through this and explain what should go on this page. Now guys, everything needs to fit on your cover page, so you need to scale your writing accordingly. Second quarter was all about forces. So a force, as it says here, is a push or a pull on an object. It's that simple. It's a push or a pull. It's measured in these units we call newtons, in honor of Isaac Newton. And it's given the symbol capital N. So every force we talk about, the units are in newtons. We spent a lot of time talking about these free body diagrams. We abbreviated them FBDs, free body diagrams. And they're diagrams which show all of the forces acting on the object. And I gave you an example to write down. This is a free body diagram. So we draw a box. We put the mass in kgs in the middle. And then we put all the forces acting on the object. So we could have an applied force, we could have friction, we could have force of gravity down and normal force up. It shows the magnitude and the direction of all the forces acting on that object. Really useful in physics, free body diagrams. We spend a lot of time talking about balanced forces. Balanced forces, like its name implies, is when there's no net force acting on the object. So for example, you've got 5 newtons to the right. Well, if there are balanced forces acting on this object, there's 5 newtons acting on this object to the left. So they balance each other or cancel each other out. There's no net force. They're balanced. We talked about net forces. A net force is when there are unbalanced forces acting on the object. So I give you an example down here. If this object right here has 10 newtons to the right and a force of 5 newtons to the left, well, now they're unbalanced, so there's going to be a net force. How do you find the net force? You always take one side, subtract off the opposing side, and that gives you the net force. So it's netting 5 newtons to the right, because 10 minus 5 is 5, and it's 5 to the right, so you need to make sure you tell direction with your net force as well. That's everything that should fit on your cover page. Let me give you a second. If you're not done, please hit pause on your video right now. Once you're done, we'll go to the second page. Okay, so let's move on. So a force, again, guys, is a push or pull. Well, guess what? All motion is caused by a force. All of the motion that we see is caused by a force. And so I wanted to kind of start here. Who was the first person to start trying to explain motion of objects? It was Aristotle. And Aristotle said that it's just natural for things to come to rest. And so if you roll a ball, it's just natural for it to come to rest. And that's how they explained it. Well, Isaac Newton came along and he changed all of our ideas about motion. He did so with 3 laws of motion. And so the next page, page 2, the inside front cover, which is page 2, I want you to title Newton's First Law. So Newton had 3 laws of motion, but let's go over the first law with this page. So again, all of this writing has to fit on your second page, so please scale it so that it can all fit. Let's define Newton's first law. It says an object at rest stays at rest. An object in motion stays in motion unless it's acted upon by a net force. Unless it's acted upon by a net force. So an object at rest stays at rest, object in motion stays in motion, unless it's acted upon by a net force. I've got 3 examples that I'd like you to include on this page. This first example, if the object is at rest originally, and then you put 5 newtons of force to the right with 5 newtons of force to the left, well, there's no net force here. It's balanced forces. So if it was at rest originally, it's going to stay at rest. It's going to stay at rest. There's not a net force. It's going to stay at rest. The second example. Now this object is already in motion. So let's say it's moving already. And now you put 5 newtons of force to the right and 5 newtons of force to the left. Again, there's no net force, so it's going to stay in motion. But if we describe its motion with more detail, it's going to stay moving with a constant velocity. It's going to stay in motion, but it's going to be moving with constant velocity. Well, now let's look at this third example where there is a net force. But let's say the object is at rest, or it could be in motion already. So either way, either it's at rest or it's in motion. Now let's say that the force is acting on it. You got 5 newtons to the right and 2 newtons to the left. Well, now there's a 3 Newton net force. So the force net is equal to 3 newtons to the right. So what's going to happen if there's a net force is that it will accelerate in the direction of the net force. And so this one's going to accelerate to the right. Even if it was at rest originally, now it's going to accelerate to the right. Well, let's say it was in motion. Still going to accelerate to the right. And so that's Newton's first law. Object at rest stays at rest. Object in motion stays in motion unless it's acted upon by a net force, and then it will accelerate. All right, please include all of that on page 2. If you're not done writing yet, please hit pause until you are, and then we'll move on to page 3. Okay, so let's continue on. Before we go to Newton's second law, though, on page number 3, I want you to title it friction. So I put the symbol for friction. It's the force of friction here. So title it friction.
Oh, dang it.
And let's talk about that for a second. So what I've done is included the formula for finding the force of friction first. To find the force of friction, you've got to know mu. This is a Greek letter, mu. And you times that by the normal force. So mu times normal force will tell us the force of friction. I know it's been a while since we've talked about this, so I want you to define these terms a little bit more. Mu, this funny looking u, is a Greek letter, mu. It's the coefficient of friction. And the coefficient of friction for smooth surfaces, so the more smooth and slick the surface is, the lower the coefficient of friction. So the lower the number will be. But let's say you have a really rough surface like sandpaper. If it's really rough, it's going to have a high coefficient of friction. So the higher the number for the coefficient of friction it will be. So that's mu. Guys, what's going to have a lower coefficient of friction? Ice or concrete? Ice. Ice is much smoother, it's slick, has a lower coefficient of friction. If it's more rough, it will have a higher one. Okay, let's go to N, which stands for the normal force. The normal force always acts perpendicular to the surface that the object is on. So for example, I've got a couple of examples here. If it's on level ground, the normal force points straight up because that makes a 90 with the ground. But what if it's not a level surface? What if it's on an angle? It still acts perpendicular, and you can draw in your 90 degree here. So does the normal force always point straight up, guys? No. It always acts perpendicular to the surface, though. Okay, and then I just got a couple of things on the bottom. Friction always opposes motion. It always opposes motion. So the first thing that you ought to do in a physics problem is figure out which way the object's moving. Then friction is going to go in the opposite direction. It always goes in the opposite direction of motion. And a little bit about what causes friction. On the bottom I put here, friction is caused by the hills and valleys of one surface rubbing on the hills and valleys of another surface. So when this surface here interacts with the other surface, you can see that they're going to interact, and it's going to cause this friction here, this opposing of motion. Even on really smooth surfaces like this countertop, if you looked under a microscope, you would see the little hills and valleys, the little pits in the counter. And so when something moves across it, it's going to catch on those hills and valleys, and that's what causes friction. Okay, friction is equal to mu times n. Coefficient of friction times the normal force. Hopefully that's a good review. If you're still writing, please hit pause. And once you're done, we'll go to the next page.
Yes.
All right, guys, let's continue on. And let's go to Newton's second law. So on page number 4, please title it Newton's second law. Newton's second law is one of the most famous and one of the most important. So let's define it. Newton's second law, if you put it into words, it says this: the acceleration of an object equals the net force on the object divided by the object's mass. Now that's put into words, but nobody ever says that for Newton's second law. What do we remember for Newton's second law? Good. We remember the equation. This is the most famous equation in physics. Force net is equal to ma. And so I'd like you to write that down. Force net is equal to ma. Now I've got a couple of examples underneath in which we'll use this equation to answer the question. So let's do this first one. It says find the acceleration of the object below. Well, this object has the mass of 5 kgs. And it's got a force going to the right of 15 newtons and a force going to the left of only 5 newtons. So let's use Newton's second law to figure out the acceleration of this object. Force net is equal to ma. Well, the net force, what is it, guys, if it's 15 to the right and 5 to the left? Yeah, the net force is 10 newtons to the right. So we're going to substitute in a 10 for the net force equals, what's the mass of it? 5 times a. Now to get a by itself, you're going to have to divide both sides by 5. And the acceleration is equal to 10 divided by 5, which is 2. What are the units for acceleration, guys?
2 seconds.
2 meters per second squared. Meters per second squared is always the units for acceleration. Well, let's try asking it a different way. What if I asked you this question on the final exam? I said, find the net force on an object that has the mass of 100 kgs and is accelerating at 5 meters per second squared. So now I give you the mass and the acceleration, and I want you to find the net force. Well, again, I hope that you will just use Newton's second law. Force net is equal to ma. The mass was 100 kgs. The acceleration was 5. So if you do 100 times 5, it's 500. But that's telling us the net force, so it's 500 newtons. And so that net force would have to equal 500 newtons. Okay, a couple of questions for you before I move on. Here's Newton's second law. What's going to accelerate at a greater rate? Kicking a soccer ball with a certain force, or kicking a bowling ball with the same force? Which one's going to accelerate more? The soccer ball. True. We all know that. The soccer ball is going to accelerate more. But why is the soccer ball going to accelerate more?
The mass is...
Because the soccer ball has less mass. Good. Soccer ball has less mass. All right, guys, that's Newton's second law. Hopefully that comes back into your memory and you understand it. If you're still writing, please hit pause on the video. Once you're done, we'll move on to page 5. Okay, guys, let's now go to page 5. In page 5, I want you to title it Newton's third law. So this is the last of Newton's laws of motion, Newton's third law. So let's define it. Newton's third law says, for every action, there is an equal but opposite reaction. So Newton's third law, guys, forces always occur in pairs. There's an action statement and there's a reaction statement. So I've got a couple of examples here. On this first example, I'd like you to draw a baseball bat and a baseball. Baseball bat and a baseball. This is a good scenario to kind of look at Newton's third law with. If my action statement is this, the bat hits the ball. What's my reaction? What's the pair force to that? The ball hits the bat. So you just say it the other way around. Equal but opposite. Now guys, what if the bat puts a 1,000 Newton force on the ball? How many newtons of force will the ball put on the bat? The same, but opposite direction. It's still going to be 1,000 Newton force, but in the opposite direction. Okay? And so I've got another example that quantifies Newton's third law. And so I'd like you to draw a picture of a car that has a mass of 2,000 kgs. And it's traveling to the right. And then I'd like you to draw this semi-truck with a mass of 20,000 kgs, and it says semi right here, and it's going to the left. And let's say that they collide with a force of 4,000 newtons. So that's what they collide with. Now I've got a couple of questions. On part A, I say, what is the acceleration of the car? Okay, if we're looking for acceleration, we're going to use Newton's second law, force net equals ma. So the net force, well, it collided with the force of 4,000 newtons, so my net force is going to be 4,000. Equals the mass of the car was 2,000, so I'm putting that in here, times its acceleration. Now, the force on the car is going to go to the left. The net force is going to the left, so I put a negative 4,000 in right here. And so when you solve for A here, you divide 2,000 on both sides. The acceleration of the car is going to be a negative 2 meters per second squared. And so now let's see what happens with the semi. On part B, I say, what is the acceleration of the semi-truck? Again, we're going to use Newton's second law, force net equals ma, to solve it. But guys, the net force is still 4,000. But for the semi-truck, the force is going to be going to the right. So that's positive. Is equal to its mass, which was 20,000, times the acceleration. To get A by itself, you divide both sides by 20,000. And so 4 divided by 20,000 is equal to 0.2. And so the acceleration of the semi-truck is 0.2 meters per second squared. Now here's a question. How come the car accelerates so much faster than the semi-truck? Because it has less mass. And we can actually quantify this. It looks like the car is accelerating 10 times more than the semi-truck. Why is the car accelerating 10 times more than the semi-truck?
It's 10 times lighter.
Yeah, the semi has a mass that's 10 times more than the car. And so hopefully you can see how all of that works with Newton's third law. Forces always occur in pairs, equal but opposite. And so we can come up with an action and a reaction statement. And also you can quantify it if you needed to. That's it for Newton's third law. So if you're not done writing, please hit pause in your video. And once you're done, we'll go to page 6. Okay, so let's go to page 6 now. We're done with Newton's laws of motion. And so let's review a few more things that are very important. I want you to title page 6, Newton's universal law of gravity. So Newton's universal law of gravity. And I just put here at the top that it's used to find the force of gravity between two objects anywhere in the universe. So this is what's cool about Newton's universal law of gravity, is that you can use it to find the force of gravity between two objects anywhere in the universe. Okay, I then wrote down the equation. The force of gravity is equal to this constant big G times the mass of one of the objects times the mass of the other object divided by the distance between the objects squared. Please remember to put a square there on the distance. There's this inverse square law happening with Newton's universal law of gravity. Okay, then I've got an example question, and here's what I would ask on my final exam. Something like this. If I've got two planets here, this is planet number 1 and this is planet number 2, and I say that there's a force of gravity between them of 1,000 newtons right now. But then let's say we change things a little bit. I say, what would the new force of gravity be if you doubled the mass of each planet? So you double the mass of each planet, and then you move them 3 times farther apart. So you separate them 3 times farther apart than what they are currently. How would you answer this question? Well, I hope that you would write down this equation. Okay? And then let's see how each variable is changing. Is big G going to change? No, that's a constant, so I put a 1 in right there. How is M1 going to change? Well, I said we were going to double the mass, so I'm going to put a 2 in there for M1. The second planet, M2, you're also doubling its mass because you were doubling each of the objects, so I'm going to put a 2 in there. Divided by d squared. Now d, if you're tripling the distance, you put a 3 in for d, but then you still got to square it. So that becomes 9. So on the top, 1 times 2 times 2 is 4. On the bottom, it's 9. So guys, is this your answer? Is it now 4/9 newtons?
Almost 4/9 as much.
It's 4/9 as much as it was before. So as much. And so this is 4/9 as much. Well, how would you figure that out? Well, you take what it was before, 1,000, and times it by 4/9. If you do that, you get 444.4 newtons. Now, a very important question. Why is the new force of gravity smaller than the old one?
Because you added more distance.
So yeah, but we times the mass by 2 in each case. So what has a larger effect? Changing the object's mass or changing its distance?
Distance, because you have to square it.
Good. It's distance, because it is squared here, is going to have a larger influence on the force of gravity. Very good. So if you could do a problem like that, I think you're doing great with Newton's universal law of gravity. All right, if you're still working, please hit pause in your video right now. Once you're done, we'll go to page 7. All right, a couple more things to review. On page number 7, I'd like you to title it Coulombs Law. Coulombs Law. Charles Coulomb, he was the physicist who figured out how to find the magnitude of the charge of the force that exists between two charged particles. So it's used to find the electric force between charged particles. I'd like you to write that down. Okay, so it's used to find the force, the electric force that exists between two charged particles. Here's the equation. Okay, the force electric is equal to this constant K, lowercase k, times Q1 times Q2, all over d squared. K is a constant. Q1 is the charge of one of the particles, Q2 is the charge of the other particle, and d is the distance between those particles. Then I've given some examples over here. Q1 is positive and Q2 is positive. Guys, do two positively charged particles attract or repel each other? They repel. They're going to move apart. So this is going to move apart from each other. What about two negatively charged particles? They repel as well. So again, they're going to move apart. But what if you have oppositely charged particles? So Q1 is positive and Q2 is negative. That's going to be an attractive force. And so they'll move closer together. So here's my example question. What will have a larger effect on the electric force? Is it A, doubling the charge of Q1? Or is it B, doubling the distance between the two particles? And I'm hoping that you're saying B is the correct answer. And again, the reason that distance has a larger influence on this force is that you're squaring it on the bottom. So because you're squaring it, it's going to have a larger influence on the force. Okay, that is it for Coulombs Law. Guys, I hope that everything makes sense. If you're still writing, please hit pause on your video, and there's just one page left. So when you're ready, hit play and we'll go to that final page. Okay guys, let's go to the final page and the final topic to review in this little booklet. I want you to title your this is the back cover page now, page number 8. I want you to title it Energy. We talked a lot about energy, guys, and one of the things that we talked a little bit about was heat. I want you to remember that heat always flows from hot to cold. So it's the transfer of energy from a hot object to a colder object. So it always goes from hot to cold. Well, it can be transferred between two objects one of three ways. So heat transfers by either, number one is conduction. Conduction is where you actually physically touch the other object and there's a transfer of heat between those objects. So if they're touching, that is called conduction. So if you touch the hot stove, that heat is going from the stove into your hand by conduction. Okay, then the second way that heat can be transferred is convection. Convection, if you remember, we talked about, it's the transfer of heat through moving fluids. And we use the example of the magma in the Earth's mantle. Next to the core, it's really hot. And so it expands and causes it to become less dense. It expands and rises toward the crust. When the crust, it cools down, and then it contracts and goes back down toward the core. And so it sets up what are called these convection currents. And that's what convection, that's how it moves with convection. The third and final way that heat can be transferred is through radiation. Radiation is really cool because it can go even through space. So over a distance. If you're standing next to a campfire, you're feeling that heat radiate toward you through the air. Or when you go outside and you stand outside on a sunny day, you can feel the sun's heat. It's radiating through space, and that's how you're feeling the heat. So one of three ways: conduction, convection, or radiation. Then we talked about these three concepts here with energy. The potential energy. It's equal to mgh, the mass, times the acceleration due to gravity, times the height. This is stored energy, so energy that is just stored. Kinetic energy is equal to 1/2 mv squared. This is the energy of moving objects. So if the object is moving, it's got kinetic energy. And then we talked about, finally, mechanical energy, or total energy. It's equal to potential plus kinetic. And I've drawn this example over here, this pendulum. It's a great example to use with energy. At points A, B, C, and D. Well, A is at the very top. So all of the energy that exists at point A, if it's at the highest point, it's not moving, it's all potential. Let's skip B for a second and go to C. At the bottom of its path, there's no more height. There's no kinetic energy. There's no potential energy. It's all kinetic at this point. It's moving the fastest at point C. And then it turns that kinetic energy back into potential energy. So at D, it's all potential. Now, guys, one last question. At point B, what kind of energy exists at point B? Well, it's going to be half and half. Half potential and half kinetic, because it's in between these points A and C. So half of it's potential and half of it's kinetic. Guys, and hopefully that makes sense and that kind of gives you a better idea of what we studied in second quarter. So, again, please make this little booklet. You can use it as a way to review for the final exam, and hopefully it helped you learn something.